Good morning. My name is Michael Habeler. I'm from Austria. I'm one of the founders of the Machinekit project. Another one is here, Alexander Rössler, beside me. You will hear him later. I was asked to give an introductory talk about what Machinekit is and what's special about it. And I have no real introductory talk about Machinekit, so I'm repurposing another talk I gave at a Ross Industrial meeting in Stuttgart earlier this year. But it brings about the key aspects of Machinekit across quite well. First, let me just explain a little bit of history and how it came about. Machinekit shares a lot of history with a so-called Linux CNC project, and that goes back to the Reagan era. By that time, there was the fear that Japanese are coming. They're killing the American machinery industry with their high-precision, low-cost gear and so forth. So that was the craze. And as a government, the typical solution you take in that situation, you throw money at the problem. In that case, do some research, and guess what? There was an institution which took the money. That was the National Institutes of Standards, which also does software research. It's in Maryland. So they took the money and they proposed to build what became a prototypical CNC application, back then called the Enhanced Machine Controller. So going for a research prototype, what that contained was an interpreter for the G-code language, which goes back to the 50s. G-code is, probably most of you will be familiar with it. It's a simple language to describe a trajectory of a tooltip made from lines, arcs, Bezier curves, splines, and so forth, which describes typically the cutting path of a mill or any other automatically driven machine. So that language describes the path that needs to be interpreted and translated into movement commands for the machine. That planned path, that desired path, is translated into a trajectory, which is a curve in Cartesian space attributed with time, by which time should the tooltip be at which position. So these are the key components. There was early research in kinematics. Kinematics describes the relation between the tooltip of a given machine and the position of the joints of the machine. Now, if you have a simple mill, each joint corresponds to a Cartesian coordinate. That's what we call a trivial kinematics machine. So in that case, the joints corresponds to the Cartesian axis. However, if you employ a robot arm, like let's take my arm as an example, I have a couple of joints here, 1, 2, 3, 4. The positions of these joints do not correspond to the Cartesian position of my fingertip. So there's a transformation necessary between the position of my joints and the position of the tooltip or fingertip in that case. That problem is called the kinematics. That is specific for a special machine. We do planning in the Cartesian space, but the machine operates in what we call the joint space. That is what's moving in the machine. So that was early research in that. Prototypical user interfaces, and also a rather primitive hardware middleware layer to connect these all together. Now, the very first, at the end of all that process, you need to talk to hardware. Okay? Drive motors, read sensors, positions, set actuators, LEDs, talk to user interfaces and all that. And in the very first prototype, the way they did that was, okay, you describe your machine as a C program or C++ program, and you compile it. Yeah. So you have one binary for one machine, and this is it. And if you add a switch or a sensor to the machine, then you have to rewrite the program. So as you can imagine, that's a somewhat inflexible interface. But as a research prototype, it was okay. They showed off their prototype, Enhanced Machine Controller 1. It runs only on PCs. It's mission accomplished, and off we are to the next research contract. So that's how that works in academic research. Eventually, since all this was funded by public money, the software by definition was under public domain. And so it fell out of the research environment, if you will, and became adopted by a group of folks which mutated that into what became Linux CNC. So that's the origin of that project. Linux CNC is operating maybe around 2000, 2001, so it goes back quite a while. The origins of EMC go back to 85 or so, even longer than that. So it's nothing new, really. It's actually quite mature thing. So that's eventually that mutated in the Linux CNC project, and Linux CNC still does exist, but eventually it hit upon them that these compiled hardware descriptions, which they inherited from the research prototype, are a rather inflexible way of dealing with an I/O configuration with a particular machine hardware. So that's a lame idea. And came a guy called John Kasunik, which had a really elegant idea of how you could adapt the software configuration to a different machinery, different electrical layouts, and he termed that part hardware abstraction layer. Now, if you ask me, that's the most interesting part of the whole Linux CNC project, and we are actually focusing very much on that, although it still is the whole CNC stack with G-code interpreter, trajectory planner, and so forth. Those parts on top are rather conventional. The interesting one is that hardware abstraction layer, because we believe that can be reused for other projects as well. As it stands in the Linux CNC project, it is completely buried within that whole large monolithic package. So we want to spin that out and make that reusable for other projects. And that's why I gave this talk to a group which deals with ROS, the robotic operating system, which is, if you will, a different top-level stack which generates trajectories. Yeah? Just that they are not very good at driving hardware, so that's why we think there's a good fit here. So that was the background of that talk. The hardware abstraction layer was a grandiose idea. I give some examples, and you will find the technique in the configurations eventually later. Unfortunately, beyond that great idea, the Linux CNC project is still showing severe signs of petrification. There are several software components in there being used in user interfaces or at the Linux kernel level, which have flatly fallen out of acceptance, which are not available even in Debian stable anymore, which says something. And in particular, since we're driving hardware at very high rates, a kilohertz and up, we cannot get by with a standard Linux kernel because those do not react in time. Those have latencies sometimes in the milliseconds range. We need what's called real-time patches for the kernel. Now, there have been various research prototypes or developments in this Linux real-time enhanced area. There's been one Italian project which just retired with the professor who did it. That's the Artai kernel by Paolo Montegazza, and that is in fact was for a very long one the only one which was supported by Linux CNC. Unfortunately, that kernel only runs on x86 platforms, meaning the whole thing is glued to the PC architecture. This is it. Yeah? So I found a couple of co-conspirators which thought that is a really unsatisfying situation. In particular, the fact that Artai is endangered in the sense that it is a one-man project. And if Paolo crosses the road and hits a bus, there goes our real-time kernel. So this is it. This brings the development to a halt. There were other options in this space called the RT preempt patches. I'm not going into detail in an introductory talk here. There's a French development, the Xenomai kernel, which runs on a whole range of platforms, on ARM, but also MIPS and other platforms. So there were other options. And me and our conspirators thought it's about time we broaden the biodiversity, if you will, to bring in other kernels to enable other platforms. The embedded ARM boards were reaching maturity and usability. The future of the desktop and the PC as we know it has a couple of question marks by now. So it was time to do something about it. We didn't come to an agreement with the guys who drive the Linux CNC project, and at some point we actually forked. That is about 2.5 years now, back from now. We forked from Linux CNC with a particular emphasis on going multi-platform, supporting a wider range of embedded boards beyond the PC platform, focusing on the HAL layer, and bringing in newer software components. We had to dump TCL, TK. Nobody's using it anymore. All the programmers are retired, which I understand TCL. It had to happen. So Alex did a lot of work of bringing Qt-based user interfaces into this space. Also, a fundamental limitation of Linux CNC is it is built on assumption everything has to run on a single shared memory CPU or one machine. There is no middleware which allows distribution over remote user interfaces, for instance. And that brings its own set of problems. For instance, sometimes graphics hardware has some very specific version requirements on Linux support, and on the other hand, that collides with real-time behavior. So that is a constant source of problems. And we believe that the best way forward is to farm out all these device driving functions into what I call a real-time appliance, which is basically some embedded board which sticks in a machine, which is driven over the network, and which does all the wiggling of pins and talking to the hardware, but it has no user interface. It's something which you talk to remotely. And that is specialized to interact with hardware. We move the user interface stuff to other platforms, maybe tablets or other devices which are better at that, maybe even phones. So making that remote capable was a key aspect. That was a long introduction to history. I'm going to give you now a short overview on how this hardware abstraction layer is, just to get the idea across. You'll go in depth more than with the other people. But I'm taking the analogy of hardware circuits, okay? Now, we talked about that compiled configuration. You describe a machine as a C program, you compile it, and that is it. In electronic terms, what that means, it's pretty much this. It's a board, it's a frozen design, okay? If it's tested, it works, but if you want to change it, you're down to cutting traces and soldering wires and patching up the hardware. That is the hardware equivalent of a compiled configuration. Okay, that's great for high volume use when you need to drive the marginal cost down. But it is absolutely a horror if you experiment or change the configuration because you don't know exactly what you're using yet. Then that type of hardware is the wrong choice. And by the way, industry has discovered that. Yeah, they're using a very modular way of controlling the real world. You see standard parts, standard DIN rails, connectors, cabling. That's all standard components, and they can be rewired easily because that compiled hardware interface is not suitable for a control cabinet. So what you'd really like to have at the configuration level is something like that, a breadboard where you can plug together components, you wire them, but you do that at the software level. Yeah? What we would like to have is the equivalent of a breadboard, but at the software level. So that would give us some stock components. It would give us reusable hardware drivers, like talking to the outside world. Also the problem of packaging the thing with a particular Linux version for several platforms, that's a reusable part. And eventually you want to talk to this device from the outside, from the controlling instance, from the user interface, by sending it commands. And that part is specialized on driving the hardware. And ideally, you'd be able to observe this thing in action by connecting a scope. Now, with real circuits, you do connect a real scope. In this space, we have a software scope which can actually diagnose most of the problems. Of course, it doesn't go as high speed as a real scope, but in this space of motion control, where your events are in the frequency range to maybe up to 50 kilohertz, it's quite a reasonable tool to have. So that is the set of ideas. You take standard components, you assemble them, you scope them until they work, and then you package them up. Now, that is the electrical idea, if you will. I will give you now an example on how you mutate this idea into a HAL setup. As an example, I'll take what is a part of what I call a typical motion pipeline. A motion pipeline goes from a trajectory, which is a curve in joint space, movements in joint space. It's typically line segments or arc segments or Béziers. And that is handed over to hardware. There's one of these curves each for each joint, and they're played out in parallel to the hardware. Okay, and that is a process which is rather time critical because it introduces noise otherwise into the process. So you have a feeding layer which could be our G-code interpreter if it's the classic Linux CNC stack, but it could be also something else like that robotic operating system, which, surprise, also generates joint trajectories, because that is a very common API at the motion control level. It's by the way, if you do interface to industrial drives, that's also the API. If you do EtherCAT, or that's basically, these are joint interfaces. So such a trajectory might be segments which are rather long, like a slow move over a long distance, so that might run for 20 seconds, and then it goes into a corner, which is just a very tiny arc, and then it again does a long move. So these segments are not equidistant in time, equitimed, but they have different duration. These segments are attributed with time. So, and the playout pipeline takes such a segmented curve and translates it into electrical signals to drive a particular joint. Now, for a given machine, like a 3-axis mill, you would have 3 instances of that whole pipeline for the X, Y, and Z joints, of course. And the driving layer generates all 3 axes, or joints in that case, because it's a trivial kinematics machine, in parallel. So the first step you do is you have to interpolate these segments over time for a given point in time. So as the machine moves through a long linear move, for each cycle advance in time, you need to calculate the next position for that particular joint. And that is what an interpolator does. It takes such a segment and it takes a point in time as an input, and it gives you the position at that time. It also does certain jobs which are good for the machine. For instance, if there are discontinuities in the curve, it smoothes them out, and that reduces the mechanical jerk and load on the machine. So the interpolator takes that segment, takes line segments, smoothes them up, and gives us time samples. So for each point in time, that whole thing runs cyclically, maybe at 1 kilohertz, maybe at 10 kilohertz. For each cycle, we get a new position value at the output of the interpolator stage. And now we need to take that and make the motor move. So the way you typically do that is with servo loops. So you have a motor which is coupled, which drives a particular joint, and you have a position encoder which feeds back the actual position, okay? Because you don't know, especially after turning on the machine, you typically don't know the position. So that is the classic control loop. You have a PID loop which controls the hardware stages, that might be an H-bridge, and PWM stages, which actually drive the motors at the end. And you have a feedback, maybe a quadrature encoder, which gives you the actual position of the joint. So that's basic control theory, though I don't think we have to expand on that. That's just the logic. So you create equidistant samples, you feed it into the servo loop, and off you go. There isn't much more than that to it. But you have a couple of parts which are reusable. Those are quite generic. The interpolator, the PID loop, the encoder, they don't care what they are actually connected to. So you can take them and assemble them in new forms. That whole thing runs in a time-critical context, and that's why we have a bridging function, which is a very low latency queuing device between the non-real-time space and the real-time space. We call these devices ring buffers, which are planned for feeding commands and status in both directions, from the real-time to the non-real-time space and vice versa. So so that's the function. I don't think this is a very complex thing. Now let's break that down into a hell configuration, and you will see the analogy with the circuit diagram quite quickly. The first thing is we need to create instances of these objects which we're using here. So we create a new ring buffer, and we do that by using a scripting language which is part of Machinekit. It's called hell command. It's a very simple command language. So we create a new ring buffer. We give it a name. That's the feed.0. 0 is the joint number which we're operating on, because we might have to do that several times for each joint. We might have a feeder component which talks to the outside world, be it the G-code interpreter or the robotic operating system. And we tell it, by the way, you stuff your commands into this queue. Yeah? That's what the argument is about. Ring becomes feed 0. Please operate on this one. So this gives us the ring buffer and the feeder component. The next step is we instantiate, pretty much like you do in Python or C++, you instantiate an object of a type. The type is interpolator, and the instance is called IP.0 in that case. And in this case, we also tell it, please listen on command messages from this ring buffer. Okay, so that's the third line, connecting the ring buffer and the interpolator. And then we go on and create all the remaining components, the PID controller, the H-bridge, the PWM generators. And now we have these software instances. They have a name, they have a type, and they have a sequence of what we call I/O pins. For instance, a PID loop has a commanded position and a feedback position input, yeah, and a driving output. Those are pins, those are named objects. They have a type like Boolean, signed, unsigned, floating point, and they have a direction. That is exactly the same like with a logic gate, a NAND gate in a 7400. It has two inputs, they're type Boolean, and has one output, which is type Boolean. And you can connect one output to any number of inputs, but you better do not connect outputs against each other. Okay, that's the same thing in this language. This is very close to a hardware setup. So you instantiate all the objects, you stick them into your breadboard, if you will, then you wire them up, yeah, and that defines the lines between these components. At this wiring stage, there is a check behind the scenes if the driving wire and the receiving wire are compatible in the type. So you don't accidentally connect a Boolean output to a floating point input. So you'll have to do a conversion stage or something like that. So there's some type checking here and the direction compatibility checking, so you don't connect two out pins against each other, which might cause overheating. So you wire them up, and the last stage is you need to get the whole thing to life. To execute that, the execution model of HAL is a cyclic model, meaning it runs a chain of functions, maybe, 1,000 times a second is a standard rate. Now, how you do that, each of these components exports the pins, we talked about there, we wired them up here, and they also export processing functions. For those of you who program, that's a named callback in the component. And these processing functions have a string name as well. You assemble them with a thread and say, this thread runs at that rate, and it calls first this function, then this, and this, and this, in that order. Okay? So the last step is you instantiate a thread, and that runs with real-time properties. This is a very low jitter thread. You give it a rate, which is in that case 1 million nanoseconds or a millisecond. Then you add the functions to that named thread, and at the last step, you start it, and that releases execution. And from there on, the whole configuration is alive. It starts listening to commands here, and does the interpolation, does the PID loop, does the position sampling, but it's all built out of reused components. We have not done any programming at that stage. We've just reused standard components. And that is what you do when you adapt Machinekits to a new machine. You figure out the circuit which you need. You look up which components match my task, and most of them will be there. There are about 100 or so components, from very simple digital logic, analog logic, signal processing like low passes, high passes, differentiator, integrator, all like standard fare which you'll learn at school, if you will. Then there are more specialized components which do trajectory planning and so forth. So most of the job can be achieved by reusing stock components. If you don't, there's a C and a Python API to create your own components for a special purpose. It is relatively rare that you actually have to do that. Typically, you need to do this for new hardware, because where the whole thing interacts with the hardware, that is very platform specific. So some of these HAL components are called HAL drivers, and they actually interact with the hardware. Bringing the whole thing to a new platform typically involves new hardware drivers, a new method, new GPIO numbering, that kind of thing. Yeah? Device tree operations, typical very low-level Linux tasks which are involved here. So that is the most of the job, bringing it to a new platform. Once in a while, you need a specialized component because it cannot be easily assembled out of existing ones. And for that, there's a standard API. So that, I hope I brought across this, the basic idea here. I'm going to show you now a video that is, Bas is going to explain that, because that is the incarnation of that motion pipeline which we just talked about.
I'll just talk with what is happening, because later in this day I will give a demo, and I will run through the entire chain what is happening. So I'll just keep it short and to the point, because I will elaborate later on. What you will see here is the setup, how a trajectory from ROS, segments, are being used to generate pulses. So you will have these stepper motors, which will be run by Machinekit, but the input for that will come from ROS. It's like the G codes normally in a CNC application will be converted to, will be interpolated. So if you have an arc, it will be cut down in small straight lines. And these straight lines, they are being interpolated and put into the configuration which will then make sure that the pulses will actually happen. So what you're seeing here, on the left side, there's the ROS. ROS has some standard robots configurations. So I've written a small program which does a few moves with a robot. ROS generates these messages, and these messages, we will listen to the message, and then we will interpolate those segments. That's the lowest screen on the left, where you will see the path being generated. I've made this video with a few motors on the top. I brought them with me, so you will see that the moment that the robot in ROS starts to move, the motors are being driven by Machinekit. It's a bit hard to see, but the HAL scope on the left in the bottom shows the trajectory. Ah, okay. Thank you very much.
Here you see it. Yeah.
Yeah. So here you will see the values of that joint position changing with time. Let's do that one more time. think that's part of the demo.
Fair
Yeah?
enough.
Yep.
Let me go back to the last slide and we're done. Should I continue? We're done. Thanks. I hope we got across the principle on how you configure that thing. You think up a circuit, you map it to HAL components, you wire them up, and then you run them. Now, just to wrap this up on what platform does this run? Unfortunately, as a project, we are being perceived as a BeagleBone project, which is not the case. It is actually portable over several real-time Linux kernels and a whole range of architectures. So it runs on x86, AMD 64, anything ARM, hardware floating point, ARM v7 or later. So Raspberry 1s need not apply, Raspberry 2 or later is okay. That has to do with support for atomic operations at the hardware level. It runs on a range on kernels. If you drive a process which is not time critical, you of course do not need that real-time kernel, which gives you more options as for the platform. Now, many of these platforms already have I/O devices, GPIO pins, various buses you can connect to. But embedded devices are typically, these I/O pins are connected to a ball of the die directly. So they have very poor I/O isolation, no level isolation. It's sensitive to static and so forth. So to come from a plain system to something which can be deployed in an industrial environment, you typically need I/O tentacles which isolate that poor thing from the noise of the mechanical and electrical environment outside. So one form of peripherals which are very popular both with Linux CNC and Machinekit are the products by a Californian company called Mesonet. What they produce is cards which embed an FPGA and can be connected to what they call daughter boards over a standard bus. Those are isolated, optocoupled, decent connectors, not sensitive to static and all that. So that takes care of the I/O isolation problem quite well. And the FPGA firmware on these cards actually makes for very good signal generation quality for motion purposes, for driving steppers, PWM GAN encoders, and so forth. So those are quite popular. Mesonet started with PCI cards for PCs. Those are still in use. There are other forms of connectivity like Ethernet, SPI, some other buses. One development which we've been working on in the Machinekit project, which we have not published yet very loudly except the blog post, is in the last few years a type of platform has been appearing, combined systems on chip, typically ARM processors, with an FPGA on the same die, a field programmable gate array. And that allowed us to take the firmware from Mesonet, which already has excellent support in the Linux CNC/Machinekit HAL space, and bring that onto these platforms. So this board actually runs encoders, step GANs, and so forth with 50 megahertz on the FPGA, and the ARM core is not involved anymore. It is actually becoming very time uncritical. We got this to work with the Altera SoC FPGAs. That's one. And the other variety is the Xilinx Zinc boards, which is the competitive product, the competitor's product. Those two companies account, I think, for 90% of that market. And so that covers most of it. And we already have it on the Xilinxes as well. So we think that this type of platforms, they redefine price-performance ratio by at least an order of magnitude. And one of our fellows has made adapters which you can plug this Altera board in on the one side and connect it to these I/O extenders from Mesonet, which give you a decent industrial flavor connectivity. So we think that this will be actually the future in terms of high performance interfaces at very low cost platforms, and that's where we want to go with the Machinekit project. That is ready but not published. That works in single instances, but we have not assembled the SD card image for that yet. So the plan is to have that sometime this summer, so you can download it, and it actually does the time critical part on the FPGA. So this was a short overview of our project, and I tried to convey the idea on how the configuration part works. I guess I've talked too long anyway, so I will stop at that point, and I'm happy to take any questions.